Hello friends, in this video I'd like to solve the following problem from the Romanian District Mathematical Olympiad for 11th graders 2008, problem number 1. We wish to prove that the determinant of a squared plus a plus the identity matrix is greater than or equal 3 over 4 times 1 minus the determinant of a squared. For any 2 by 2 matrix A with, of course, real entries to talk about inequalities. It's a very nice problem from linear algebra. Here are my hints. Well, although this is, we are talking about matrices with real numbers, we will be using complex numbers. Let omega be not equal 1 and let omega cubed be equal 1. We know that there are two complex numbers omega which satisfy these two conditions. They are called the primitive roots of the primitive cubic roots of unity. Notice that then z squared plus z plus 1 can be written as z minus omega times z minus omega squared. Next, notice that this characteristic polynomial, which I will denote by chi of z, which is defined as the determinant of a minus z times the identity matrix, it is some quadratic polynomial. In fact, B is the trace of matrix A, C is the determinant of matrix A, but we will just notice that this is for sure a quadratic polynomial with real coefficients B and C. Next, use this fact about these primitive cubic roots of unity to factorize a squared plus a plus I as a minus omega I times a minus omega squared I, and use the fact that the determinant of product of matrices is the product of determinants. So give this problem a try, and I will see you in just a minute. Alright, so you know what, maybe let's start with this fact, that if I have a primitive cube root of unity, then I have z squared plus z plus I can be factorized in this way. Well, this should be obvious, but let's prove this little thing. Proof. Maybe let's write it that it's a claim. Proof of this claim. Well, notice that z squared plus z plus 1, it can be of course written as z cubed minus 1 over z minus 1, provided that z is not equal 1. Of course, and notice that both omega makes this denominator vanish, and omega squared also makes it vanish. So it can be written as z minus 1, z minus omega, z minus omega squared over z minus I, z minus 1. And z minus 1 is gone, and after doing that, we are left with this, which concludes the proof of our claim. Alright, so now let chi of z be equal to the determinant of a minus lambda I. Is the characteristic polynomial. Not lambda, but z, since I'm calling my variable z. Notice that that means that this can be written as the determinant. You know what? Let's write that A is a matrix A, B, C, D. And notice that then this determinant is the determinant of A minus Z, C, B, D minus Z. And notice that it can be written as A minus Z, D minus Z, minus BC. Notice that this is for sure a quadratic polynomial with real coefficients. So it can be written as z squared plus b and c were used, so maybe let's call it a different letter. S z plus t, where s and t are real. In fact, it can be easily demonstrated that S is the trace of matrix A, T is the determinant, but I will not use it, so let's keep it as it is. Alright, and now, what I will do, I will compare, maybe, you know what, let's start with the right-hand side. On the right hand side, we have 3 over 4 times 1 minus the determinant of A is squared. And notice that what is the determinant of A? The determinant of A is just chi evaluated at 0. So it is 3 over 4, 1 minus t squared. Alright, now left hand side is trickier. On the left hand side we have a squared, the determinant rather, of a squared plus a plus I. Now, using our factorization, it's the determinant of a minus omega I, minus omega squared I. Well, it's pretty easy to verify that, because here we have a squared, then we have minus omega squared a, minus omega a, plus omega cubed. It's exactly the same, because the identity matrix commutes with any matrix. Now, the determinant of the product of two matrices is the product of determinants. Which is well and good. And now let's notice that what is a minus omega I? Well, it's the characteristic polynomial evaluated at omega. Characteristic polynomial evaluated at omega times the characteristic polynomial evaluated at omega squared. And now let's do our tedious calculations. This product, it's what? It's omega squared plus s omega plus t, omega squared, so omega to the 4th power, plus s omega squared plus t. Now, let's before multiplication, let's write it in the following way. Notice that omega to the 4th power, omega cubed, is 1. So we have s omega squared plus omega plus t. And now we need to multiply everything by everything. So we have s omega to the 4th power plus omega cubed plus t omega squared plus s squared omega cubed plus s omega squared plus st omega plus st omega squared. Need some space. Perfect. What's left? St omega squared, t omega plus t squared. Now, let's simplify it. Well, s omega q to the 4th power is the same as just s times omega plus 1 plus t omega squared plus s squared plus s omega squared plus st omega plus st omega squared plus t omega plus t squared. Right, and now let's combine two terms. First, here we have t omega squared, s omega squared. So let's combine it. And here we have st omega squared. So we have s plus t plus st omega squared. What else? Here we have s omega, st omega, and t omega. So we have plus s plus t plus st omega. And what's left? Well, 1 plus s squared plus t squared. Alright. Right. And now s plus t plus st can be factored out. And notice that I have omega squared plus omega. And I will do a trick. I will write omega squared plus omega plus 1 minus 1 plus 1 plus s squared plus t squared. And notice that what is omega squared plus omega plus 1? Well, it was demonstrated that it is 0. So we have s plus, we have rather 0. So we have what? Minus s minus t minus st plus 1 plus s squared plus t squared. Perfect. And remember, what we wish to demonstrate is that this should be greater than or equal, 3 over 4 times what? Times 1 minus t squared. Alright, and now let's proceed by equivalent conditions. The following inequalities are equivalent. The following are equivalent. This inequality is equivalent after multiplication by 4, minus 4s minus 4t minus 4st plus 4 plus 4s squared plus 4t squared greater than or equal 3 minus 6t plus 3t squared. And now maybe let's write it in the following way. Let's group t first. 4t squared plus 3t squared, so it's t squared. What else? We have plus 6 times t, but here we have minus 4t, so it's plus 2 times t. So this and that is covered. And also we have minus 4st, so maybe let's write it. It's 4st. Alright. And everything else is without t. So we have plus 4s squared minus 4s plus 4 minus 3 is plus 1. Should be greater than or equal 0. Should be. What is it? Well, notice that we can do the following. T squared, here we can put minus 2 in front, so we have 2s minus 1 t. And here we have, what exactly? 2s minus 1 squared, greater than or equal 0. And notice that this can be written in this way. It's t minus 2s plus 1 quantity squared. And this is obviously true. This is obviously true. So our inequality holds, which closes our proof. It was a very nice problem because we were using cube roots of unity, primitive cubic roots of unity. And I suggest that you become familiar with these types of manipulations if you are preparing for some type of competition where some linear algebra knowledge is expected. So use characteristic polynomial, because notice that all of that was factorization of the left-hand side. To be possible, complex numbers were needed to complete our factorization. And notice that I have expressed both sides in terms of my characteristic polynomial. And that was the key to solving this problem. And that is it. So thank you very much for watching. I hope that you've learned something new this time. I hope that you were entertained. And I will see you next time. Goodbye.